Hello and welcome to Physics Unit 1 Lesson 3 online. Tonight we're going to be working on linearizing nonlinear data. It's just a continuation of what we've been doing in class. And so, again, it's the same principles as y equals mx plus b, but now we're going to look at things that don't follow the y equals mx plus b line. So what happens when the data cannot be fit by a straight line? The following is an example of that. It's the graph of a current for a circuit with light bulbs of different resistances. So we'll go down here. Okay, so when we took our data, we took resistance versus our current here, and we get a pattern that looks like this. And when we use Logger Pro to try to graph the data, clearly the data does not fall on the line like we like it to. So is a linear line a good fit? Not really. It doesn't fit at all. But the thing is that we got to ask ourselves as a researcher, because that's what science is recognizing patterns, is there a pattern to this data? Okay, and I would argue that there's a very clear pattern, as you can see here. It's just not linear. So I would say probably, and we can see a pattern. So the conclusion that we can draw now is they probably are related, but not linearly. And so again, this is the process you got to go through as you look through data throughout our different units. Okay, that's where we're going to need to try a different fit, but the question is, what should we use? Now, this is not a new topic, it just is in your science classes. And so I've come up with a quick way, a kind of a quick guide for how to access your math knowledge. And so I've got a reading called Curve Fitting. I'm going to jump cut over to that now, so that you can see how I would go through this if I'm a student not knowing what data that I should use. So I'm going to jump cut over to that. So here we are with our Unit 1 reading. It's not actually called curve fitting. I apologize. It's called graphical methods. In this packet here, we're going to need to find Step 1 is locate this packet. Step 2 in our step is to find a graph that looks similar to ours. Well, this graph doesn't look similar to ours, so we don't want to use it. No. Okay, now this one looks similar, but I'm not going to give up yet. I'm going to go ahead and try to find another one. Sometimes I sing a song while I'm doing this, it's from Sesame Street actually. Goes like this. One of these things is not like the other. One of these things just doesn't belong. Nope, those aren't what we want. So our best fit, which most looks like our graph that we're looking at with the amplitude or the current versus resistant, looks like this one here. And it appears to be a hyperbola or an inverse function. So I'm going to go ahead and jump cut back to my PowerPoint slides. So here we are again, and like I said earlier, I just want to make a note. I did change this term here to graphical methods. Okay, so we flipped through it, we found one similar to ours, and ours appears to be a hyperbola or an inverse function. Alright, that's the easier part. Alright, to straighten resistance, we look at that sheet, and it tells us that we need to do 1 over that which is on the x-axis. Okay, so that'd be 1 over resistance. Okay, now the tutorial will show you how to use Logger Pro to do this. It's not complicated. You don't have to do it by hand. There's a easier way to do it, and the tutorial that you follow up with this will show you how to do it. So I took the liberty to do that. We're still on step 3. Notice here I have my resistance down here, 1 over resistance, and now my current. Okay, now the question is, does that look better? Well, let's go ahead and try it and put a linear fit. Like Macho Man says, oh yeah. So here we go. I went ahead and used Logger Pro to use the linear fit. Again, that'll be in the next tutorial how to do that. And sure enough, now when we look at this, the line goes through my data. Now the question is, some get confused by this and are like, well, did we just change the nature of this relationship? Well, no, it's still an inverse relationship like we saw, but if you look down here, now it says it's proportional with the line to the inverse of resistance. So it's still the same game. It's still the same nature, except now we're just representing this thing in a different way. Okay, so and then you got all the other information like we normally do, where we got our slope, our slope here, our y-intercept, etc. Now we're going to go ahead and do like we have been doing. This is a review point. We're going to go ahead now and substitute in our variables. So let's go ahead and try that. So like step 4 says, find the mathematical equation and substitute in the variable. So from the graph on the y-axis, okay, we have current. On the x-axis, we have 1 over r. And then up here, we have our slope and our y-intercept. Okay, and I just recorded those down. So y is current, m is 1.21.4 amp ohms divided by 1 over ohms, which is interesting. So notice resistance was ohms. Now you got to invert the unit as well, and so you end up with 1 over ohms, and so you end up with amps over 1 over ohms, and you simplify that to amp ohms. Again, I showed that in the previous one how to simplify a complex fraction. Okay, so but again, you always want to simplify units when possible. Makes everything easier. So x is 1 over resistance, and the y-intercept is 0.1832 amps. So the equation looks as shown here. So the question is, should we drop the y-intercept? Is this intercept close enough to 0 that we can get rid of it? And we have 2 main checks that we need to go through. All right. And again, you got to be able to do this at any given point. So here's our rule of thumb. It doesn't always work, but there's essentially 2 things I look at. The y-intercept may be dropped when the absolute value of the y-intercept is less than 5% of the slope, and if it makes logical sense. You always want to do both of those checks. Okay, so let's first of all do the math of it and see if it's even a candidate. Again, if you're really good at math, you can already see that it is. So the absolute value of y-intercept is 0.18. You take that number divided by 121, which is our slope, times your 100 to make it a percentage, you end up with about 0.15%. So 0.15% of anything is really small. So it definitely is mathematical justification to get rid of it. Now this is a new slide. I forgot to put space in there, so you're going to have to copy this down. In reality, let's do the reality check. In reality, the y-intercept is the value of the current when 1 over resistance is equal to 0. Okay. So now, since 1 over infinity, for you pre-calc and calculus people, is equal to 0, that's how you get the number 0, thus your resistance is equal to infinity. So for current to equal resistance, you must have an infinite amount of resistance. If you want me to go through that again with you tomorrow in class, I can. But it's the inverse of what we were doing in the last set. So an infinite amount would give you current equals 0. Well, and that does make sense if you're looking at an inverse. That's the nature of, let me go back all the way to here. The inverse is that for the value of anyway, we'll go over it again. If you want to go over it again, I lost my train of thought. So for current to equal 0, yeah, we'll look at it like this. So for the current to equal to 0, which is approaching 0 here, right? What does my resistance do? My resistance goes off towards infinity. So that should make sense to you. If that's a new idea, you'll learn about it in pre-calc or calculus. So let's go back here. So there is reason to get rid of it in reality, so we're going to choose to get rid of it. So we should drop it in this case because we have the statistic and we have a reason to. So only drop the slope if the line should go through 0, 0. So our new equation looks like this. Current is equal to 1.21 amp ohms times 1 over the resistance. If you want, you could put this over there, or you could just put the resistance on actually the bottom of the equation there if you'd like. Okay, so the last thing we want to do is, how do we really know if it's a good fit? So far, we haven't used any statistics. We've just been using our eye, and so it's always good to go with your statistic, let your data do the correcting for you. And so that's where we go with this correlation number. And the correlation number is the extent to which the two variables are related. So if you look back here, if you've looked, the Log of Pro actually calculates this for you. I'm sure there's a complicated equation somewhere that allows us to do this. But if you look at this, the correlation is 0.9995. Now, you want your correlation to be close to either +1 or -1, and that tells you to which the variables are related. So let's look at the original data and compare those two. The original data, the correlation is -0.85 versus the 0.9995, and so the 0.9995 is much closer than the -0.85. So we go with the correlation. So we go with our second fit based on our correlation. And that gives a statistical argument. Okay, so in words, current is inversely proportional to resistance. So as the resistance of the lamp increases, the current decreases. And again, like I said, the correlation is shown by a perfect correlation is shown either by a +1 or a -1 if it's a negative linear relationship. Now this rarely happens in the real lab. Over 0.9995 or 999995 is almost 1. So again, we go with that. So a perfect correlation shown by negative, slope is -1, and there is a professional wrestler by the name of Mr. Perfect, God rest his soul, like many of their professional wrestlers. He passed away. So I already did this, but when the data for the current versus resistance was fitted, the correlation was -0.85. For 1 over resistance is 0.995, and of course the 1 over resistance is a better fit, and it does confirm what we know in reality. It should confirm what you see, but again, it's a statistic to help you that. So here's my quick reference guide here. This is really important. The first thing when you ask for help, the first thing I'm going to do is I'm going to say, well, where are you on the 5 steps? Okay, so this is your quick reference guide. Always keep this in hand while you're doing this. So the reading is actually graphical analysis. Again, that should be changed to our graphical method. All right. Then you flip through those pages till you find a graph that's similar to yours. You straighten your graph using Log of Pro. You find the mathematical equation, substitute the variables, and then check your new fit looking at the correlation number. Okay, so what you want to do is you want to go on after this point and and complete Logger Pro tutorial 3. And then in class, we're going to do worksheet 1. Sorry, I got to go do my worksheet, unit 1, worksheet 4. We'll do that as a